In this lecture, we're going to start focusing on libraries that make it easy to read data, process data, and so on. We're still going to keep revisiting the basic elements of Python that we've been seeing in the previous 2 weeks. Loops, conditions, functions, dictionaries, all of those elementary pieces that we glue together to create our programs. But we're going to start focusing on libraries that give us functions and objects that make it easy to perform the tasks we need to automate data processing. So in this lecture, I'm going to show you one way of reading Excel files, so taking data from Excel files, reading several Excel files, organizing the data in our program with dictionaries, and then extracting parts of the data that we are interested in to matrices, to these Numpy arrays that make it easier to do computations, compute statistics, compare values, and so forth. So we're going to keep revisiting the basic elements of Python. If you are still having trouble with the basic elements of functions, loops, and dictionaries, and so on, don't worry too much, because we'll keep using them every time during these next weeks. But we're also going to start looking at these libraries. So let's use data from this site, Gapminder. This is a site that has lots of indicators for country development. It also has tools for visualization. So it's, if you like this sort of data, I recommend visiting the site and experimenting with their visualization tools. But we're going to use data from this site and do ourselves our own comparisons and processing of this data. So we're going to use data on gross domestic product, life expectancy, and population. But there are other indicators that you have there. You have these tables with the indicators for each country and for each year what the value is, and you can download the files in Excel format. So this is an example of one file for life expectancy, and you see here that you have in the first column the names of the countries, and then the following columns correspond to different years, and we have the values for each country and each year in the cells. In some cases we have missing values, so there is no data for that specific year for that country, and so the cell is empty. This is the input format. It's an Excel spreadsheet, and this is an example to illustrate a common problem, because probably most of you will need to extract data from spreadsheets, whether in Excel or some other format. So how are you going to organize data? This is something that you need to think, and it's often at the core of whatever program you're going to write. You may have to represent your data in different ways depending on how you're going to use it, but you always need to think how you're going to structure your data. So in this particular case, we have for each country, we have for each year one particular value. However, sometimes we have missing values. So we may wish to store in our data structure for each country the association of each year to each particular value. We can do that association with a dictionary. So we can have a dictionary that has the year as a key and the value associated as the value in the dictionary. And we can create that dictionary with all the years and associate that dictionary to the country in another dictionary. So basically, we're going to use a dictionary of dictionaries to store this information, so that once we have this implemented, we can do something like this. For example, we have the dictionary with the GDP data, and we ask the GDP data for Portugal, and associated with this key, Portugal, is another dictionary that has for each year what the GDP is. If we want a particular year, we can get for the GDP data the dictionary for Portugal, and in the dictionary for Portugal we ask, for example, for the GDP for 2010, and then we get that specific year. So what we're going to do is to create a dictionary with two levels, so one dictionary of countries, and for each country one dictionary of years. And this is the kind of reasoning that you need to do. How are you going to organize the data? Because this determines then how you're going to write the functions to read the data and store it in memory in your program. So let's read one of these Excel files and store the data in these dictionaries. We're going to use this Excel read library, which provides an object that can access the different worksheets in an Excel file, and also the cells inside the spreadsheets and so on. And we're going to break down the function to read the Excel file into two separate functions. One that just reads one row, so we specify from some spreadsheet what the row is that we want, and this returns a list with the values that it finds there. This is just a utility function because we're going to read our spreadsheet row by row, and intuitively it makes sense to make a function just to read the row, and we use the data that it gets us. And then loading a file, we're going to read the data in the file and return this dictionary, which has each country as a key, and for each country we're going to create a new dictionary with all the years and the corresponding value. So this is the first step. After we think about how to structure our data, how to organize our data, we're going to outline what the program is. In this case, it's a very simple program. We only two functions, but it's useful to first to have an idea how to decompose the problem into smaller parts. Okay, so now let's implement the first function. The way this sheet object works, so if we use the Excel read library to open a workbook, for example, the Excel file, we give the file name and we obtain an object that allows us to access the different spreadsheets and the different cells in the spreadsheets. So basically what Excel read does is read all the Excel file into memory and give us an object that we can use to obtain the data in that file. And now if we want the first spreadsheet, because actually these files only have one sheet and it's the first one that has the data, so we can use this method sheet by index, and the first one has index 0. Remember that in Python we start counting at 0. So this from the workbook gives us the first sheet, and now we have the first spreadsheet in the workbook. So we give this object to our function, and we also tell it what row we want. So this is the index of the row. Now this object that the Excel read module provides, which stores or which accesses a spreadsheet in a workbook, has this method cell value that we can use to obtain the value in a cell by giving the coordinates of the cell, so the row and the column. Remember, starting at 0, so the first row is row 0, the second row is row 1, and so on, and the same for the columns. So if we want the data in one particular row, we're going to loop through all the columns and create a list with the values of all the cells, of all the rows, of all the columns in that row. So to do this, we're going to create a loop that ranges from 0 to and gives us as many indexes as the number of columns that we have in our spreadsheet. This can be determined by this ncalls attribute of the spreadsheet object, so you can easily check how many columns have values in your spreadsheet. So now, starting at 0, we're going 0, 1, 2, and so on until the last column that has values. And we're going to append the value at each cell by providing the same coordinate for the row. So the index of the row is fixed, but we'll keep changing the index of the column, which is the variable that is used here in this loop. So basically, this function returns a list with all the values of all the columns in the row we specify. For example, if we get the first row from this spreadsheet, we get row 0, we have this list of values here that corresponds to the header here. So we have the name of the indicator and then the years. In this case, it's life expectancy. In this example, it's GDP, but it's the same format for the spreadsheet. So basically, we have the in this case country and then the years here. And then if we go down on the rows, if we go to the second row, we start having the names of the countries and the actual values. So this function to get the data from a row allows us to read all the row as a list. And now we're going to use that function to create the dictionary with the data for all the countries. So this one is a bit more complex, but basically these experiments that we are trying here, we're going to include them here because when we're loading a file, we receive the name of the file. So we use the Excel read open workbook to read that file into this object. This book object allows us to go through the different spreadsheets. We ask for the first of the spreadsheets in the workbook. And now we get the first row. So from this sheet, the first row, which has one cell here with some title, either countries or GDP or something like that. And then after the second cell, it lists the years for which we have data. So basically, the years will be whatever list this function returns for the first row, but ignoring the first element of that list. So we skip the first cell and we get the list of years in all the subsequent cells. Now we're going to start our dictionary using an empty dictionary. So this is a notation to create an empty dictionary. It has no data there, but it's a dictionary object. So you can add things to the dictionary and it works like a dictionary object. And now for each row starting from the second one and going all the way to the end of our worksheet. So by the same way this nCalls attribute gives you the number of columns that are filled in your worksheet, this n rows gives you the number of rows. So now we're going to loop through all the rows, starting on the second one, because if you look at the file format, the first one is just a list of the years. So now it's the second one that starts with a country and has the data. And what we do is we get the values for that row. And we know that the country is the first value on the row. So when we are looking at countries, the first value on the row is the name of the country. And everything else are the actual values, of which we have as many as the years in the spreadsheet. So what we do now here is for each of the values that we have here, we are going to to iterate through the indexes of all of this list, starting at 0 and going all the way to the end. We're going to check if the value is not an empty string, because when the cell does not have data, then this cell value function returns an empty string because the cell is empty. So we check if we have any data in that cell. If that cell is not an empty string, then we insert into this new dictionary with the year indicators a key that corresponds to the year for this particular value, which is the year in the same index as we are seeing the value. And we associate with that key the value that we have read in this row. So basically what we're doing here is we get the list of years on the first row, and then we go down all the rows, and whenever we find a cell that is not empty, we associate the year in that position along the row with the value in the same position. So this year with this value, this year with this value, and so on. And this is what we're doing here in this loop to create this dictionary. Once we have this dictionary created with all the year value pairs, we now add it to our table by creating an entry for which the key is the name of the country and associating with that country the whole dictionary with all the data for all the years. So this is how we can read the data from the Excel file and create this structure in memory. And now we can test this. So let's read the GDP file. We have our files in this data folder. The data folder is under our working folder. So we have the Python scripts in a folder and a subfolder called data with the Excel files. And we're going to read this GDP Excel file. And then if we want the GDP values for a country, we just put the country name in this dictionary, because this dictionary, the keys are the names of the countries, and we get the whole dictionary with all the years and values for Portugal. If we want a specific year, then from that dictionary, we ask the value associated with one specific key, for example, 2010, and we get the value for that year. So this is a flexible way because it deals naturally with missing values. If values are missing, we don't have the data there, and it allows us to fetch whatever value that we want from the data we read from the file. So one other thing we can do is, suppose we have files, several data files, because we have GDP, we have life expectancy and so on. We have everything in the same folder, and we want to read all the files. This is also a common problem because most of the time we have data spread out in different files, so we may want to read them all into our program before processing them. One thing that we need is to check what are the files in one folder and get the names of those files. To do this, the glob module is very useful, so you can import the glob module. This module has a function also called glob, that returns a list of all the files that match some template that you specify. For example, I want inside the data folder all the files with whatever name and the extension XLSX. So these are Excel files. And this returns a list with all the files that I have that match this template. So these are the 3 Excel files I have in that folder: GDP, population, and life expectancy. So using this, we can automate reading a number of files that we have in a folder. We're also going to use the OS library. This is the OS module. This is for with the methods and functions for operating system tasks. And this one has several functions in the path module that allow us to operate with file names. For example, the base name function gives us just the name of the file without all the path information. The split extension function, the split text, gives us a tuple by splitting the name of a file into 2 parts: everything before the extension and the extension with the dot there. So if we ask for the result of splitting the extension and just the first part, so index 0 here, we get just the base name of the name of the file without the extension. So one way of extracting just the name of the file would be to split the extension from the base name of the file. Even if it has a path, the base name will only give us the name of the file, and then picking only the first part of this split extension function, and this gives us just the name of the file. Okay, so how can we use this? We can use glob to list all the files in a folder, and then use this expression to get just the name of the file and build a dictionary with each file name, and associated with that all the data that we have. So this would be our function here. We start with an empty dictionary and with a list of all the files, of all the Excel files that are in this folder. This path join function allows us to join one path and the name of a file by automatically putting these separators as needed. So if you don't want to have to check if the separator is already provided or not, it's easy to use this function, and it just does this automatically. So we receive here the name of a folder. We create this template here, which is the name of the folder, followed by that separator and the star.xlsx. And when we put this in glob, this gives us the list of all the Excel files in that folder. And now for each of these files, we're going to add to our dictionary a key that is just the name of the file without the extension. So for example, for this file, we get just GDP. For this file, we get just pop and so forth. And we do that by using, by splitting the base name of the file and getting only the first part. So this is the name of our indicator, and in this dictionary, this will be the key, and the associated value will be the result of loading the file using the other function that we had implemented. So all this large dictionary with all the countries and all the years. And this allows us to automate loading all the data that we have in this folder. So our data is the result of loading all the files in the data folder. And now we want to know GDP for Portugal in 1980. We just do it like this. So the GDP indicator, inside this dictionary, the country is Portugal, and inside Portugal, we give the year. So this way we can access the data from all the indicators that we have in different Excel files. Okay, so this was one example. This is not necessarily the only way to do this, but this was to show you how to use these libraries, reading Excel files, listing the files in the folder, handling the names of the files and so on. And then we revisited these structures, the dictionaries, the loops, the functions, by organizing our data like this. And an advantage of this way of structuring the data is that now we have everything in memory in a single dictionary, all our indicators, and we can pick whatever we want from that data if we want to look at some time span, a series of countries, specific indicators, whatever we want, we can do it because we have all the information here. Okay, so now let's look at the Numpy library and the Numpy array. This is a very useful library when you're dealing with numerical data because it gives you these array objects that are n-dimensional matrices, and they know how to do lots of operations with the values that you have there. There are different ways you can create them. You can use this. Typically, we import the Numpy array and we give it a nickname of NP. So import Numpy as NP. We are importing this library and giving it the NP name. This is something that you'll often see if you look for code in the internet, because then we don't have to be writing Numpy all the time. And since this is such a used library, it's useful to have this short nickname. So one way of creating vectors or matrices is to use these ones or zeros functions that receive a tuple with the dimensions of the array that you want. For example, in this case, it's just a vector. It only has one dimension with length 5. And using ones, it gives you an array with 5 elements, and all of them are the number 1. In this case, using zeros fills the matrix with zeros, and if we give it a tuple, 5 by 5, then this is a square matrix of 5 rows by 5 columns. We can also create arrays by giving lists or lists of lists, and Numpy will interpret this. So if you give a list with in which the elements are also lists, and all these lists have the same length, then Numpy interprets this as each list being a row in a matrix with the number of columns corresponding to the number of elements in the list. So this would be the matrix created here. But the advantage of creating these Numpy arrays instead of just using lists is that then you can do lots of operations with them. For example, you have different types. You have the shape of the array in this attribute. You can tell what is the number of rows, what is the number of columns. You can convert types. For example, this array here is in floating point numbers. They have decimal points there, but you can convert them to integer, for example, and this will round off the values and give you just the integer values. And you can do different operations. For example, if you have one matrix like this, so this is a matrix that has 1, 2, 3, 4 in the first row, 5, 6, 7, 8 in the second, and so on. If you divide this matrix by 2, this operation will return a matrix of the same dimensions where each element has been divided by 2. So you can easily broadcast these operations through all the elements on your array just with a single instruction. And this is very useful when you want to repeat the same operation for all the elements. And this is actually more powerful than just, for example, adding 5 to all the elements. Broadcasting matches arrays of different dimensions as long as they have a length of 1 or they match in length by going from the last dimension to the first. So this is a bit difficult to understand in abstract, but it's easy to show with an example. If I add to this matrix an array with 4 values, so in this case a list with 4 values, this matrix object knows how to do this operation by broadcasting these sums over each row of the matrix. So it's going to add 5 to the first element of the first row, then 10 to the second element of the first row, and so on. And then it's going to repeat that for the second row. It's going to add 5 to the first element, 10 to the second one, and so forth. So you can use this. This is a very flexible way of broadcasting these operations and repeating the operations along your matrix with arrays of different dimensions. If you're unsure about how to do an operation like this, it's easy to look up in Google or just experiment. But the basic rule is that Numpy will match the dimensions from the last one to the first. So the last dimension in this matrix is the number of columns. The last dimension in this array is the only dimension, is just the number of elements. So these two match, and then it broadcasts this through all the rows. If you are dealing with matrices with higher dimensions, 3, 4 dimensions, 5, you can do it also. This becomes a bit more complex, but the rule is always the same. You also have functions that are useful for dealing with these arrays of numbers. You can sum all of them, compute the mean, the standard deviation, get the maximum, the minimum, and so on. And you can even do this. So if you do this like this, you're getting the aggregate of all the values in the matrix. So this is the sum of all the values, this is the mean of all the values, and so forth. But if you add an argument here specifying the axis, you can compute these aggregates by projecting along one direction in your matrix. So with axis equals to 0, this is in the direction of the rows. And when you are computing the maximum, for example, along the rows, this will give you a vector with the maximum of each column. If you want the maximum along the columns, so axis 1 is the second dimension, it's along the columns, you're going to obtain the maximum of each row because it's the maximum of this row here, the maximum of this row, and the maximum of this row. This is what you get when you're going in this direction. You can do the same for the mean, for example, the mean of all the columns, the mean over all the rows. This seems a bit counterintuitive because when you're projecting along the rows, it actually gives you the mean of each column, and when you're projecting along the columns, it gives you the mean of each rows. But this seems counterintuitive because we're only looking at it in 2 dimensions. If you imagine a matrix with 3 dimensions, then you need to specify one direction where you're doing the projection, and you'll get a 2-dimensional matrix which corresponds to projecting in that direction. So the axis here is the direction in which you are doing the projection, and then you get the result of that. Okay, so here we are seeing something that is new, which is we are providing values for a parameter by indicating the name of the parameter and the value we want to assign to it. This is one way you can provide values for the parameters of your functions, and it's especially useful if you have parameters with default values. This is just a toy example to illustrate this, but you can create functions that have some parameters which have default values assigned. So for example, mean val here has the default value of 1, maxval has a default value of 10. This means that you can call the function without giving values to these parameters. So if I just ask for test size 5, the 5 is given to the number parameter does not have a default value, but both these parameters will have their default values. We don't need to specify anything there. So since minval will be 1 and maxval will be 10, given that this one is 5, when we check these conditions, this is great. It's not greater than the maximum, it's not smaller than the minimum, so it's medium, and that's what we get. But we can give different values to the other parameters. For example, we can put a 6 here, and so this will replace the default value of minval, and now minval will be worth 6. So now we get a return of small because our number is smaller than the minimum value. And the same thing here, if we add, give 5, 1, 4, this will give 5 to this parameter, 1 to this parameter, and 4 to the maxval parameter, and now we get this branch of the condition. So if we combine this with the possibility of assigning values to parameters by name, we can create functions that have many parameters, they have default values, and the user only needs to change those default values that they don't want. So for example, if we have test size 15, 15 goes into the number, we want to keep the minimum value, we don't want to change that, but we want to change the maximum value to 20, so we just put here maxval 20. We don't need to remember what's the position of this parameter, we just specify that this is the one we don't want to use the default value. And you can do this in any order, just with the condition that arguments passed by position must come first, because Python needs to know that this first argument goes into the first parameter. Arguments that you pass by name can come in any order, but they must come after any arguments that are passed by position. So this would be valid, because even though this is not the same order that we have there, we have all of them passed by name, so there is no problem in Python understanding that this 10 is going to maxval, this 0 is going to minval, and the 20 is going to the number. Okay, so understanding this now help us understand how we can use these more complex functions in many libraries that have default values. For example, by default, if you compute the maximum of an array, the axis is none, which means that you get the maximum for all the array. But if you change that default value and specify one axis, then you're going to compute the maximum by projecting along that axis. And the same for mean, for the standard deviation, for all these functions. So we have these two advantages with Numpy. We have these functions for working with the arrays. We have broadcasting that allows us to broadcast operations through all the values. And we also have flexible ways of indexing our arrays. Not only with the regular index that we have. For example, in this case, I want from this matrix these rows and all the columns, so I can specify in each direction the usual indexing that we've been seeing, but I can also use Boolean arrays for indexing. So a Boolean array is what you get when you do these kinds of comparisons with the NumPy arrays. For example, this vector is 1, 2, 3, and if I compare it with 1, this vector's larger than 1, I get a false, true, true, because 1 is not larger than 1, but 2 and 3 are. So this is a Boolean array. It's an array, but it's not does not contain numbers. It contains these Boolean values, true and false. And I can use these arrays to index my other arrays as long as they have the same size. So this matrix has 3 rows. If I use a Boolean array with 3 values, I can use that one to index the rows, and I get only the rows corresponding to true values. So if I want from this matrix only those rows corresponding to the elements of this vector that are larger than 1, then I get this vector larger than 1 is false, true, true, and this means I only get the second and the third rows. The first one is missing because it's false. And I can even select, for example, I want from my matrix only the values that are larger than 4. So I can ask from my matrix what is larger than 4. Matrix larger than 4 will give me a bidimensional array, a two-dimensional array of booleans that has false for these here and then true for all the rest, because the rest are larger than false. When I index my matrix with this two-dimensional array of booleans, I get only the values that correspond to true in that array. Okay, so this gives us a very flexible way of selecting data, of operating with the data, of computing statistics, and so on. So let's get back to our program. We organized everything in a dictionary of dictionaries because this gives us a flexible way of storing data that we have in Excel. But now we realize that for some kinds of operations, for example, statistics and so on, it would be useful to have just an array, a matrix, with the data that we want. So for example, we could have one row for each year, one column for each country, and then we could do averages, we can do sums and things like that. And we specify which years that we want and just get a matrix with that data. So this is the approach that we're going to do here. We are not going to rewrite the program that we already did that had everything neatly organized into a dictionary of dictionaries. What we're going to do is create a function that receives that data dictionary with all the indicators, all the countries, all the years, the indicator that we want, a list of countries, and a list with the years that we want. So this is the data we want to extract, this indicator for these countries and these years. And then it's going to return a matrix that has one row for each of the years we specified, one column for each of the countries, and all the values in there. If some value is missing, because in our data some values are missing, we can use this NaN constant from Numpy, which stands for not a number. This is a special number in floating point notation that indicates that we don't have a valid number there, and it's used, for example, when you're computing the mean and the maximum and so on. Numpy ignores these numbers. So this will be our function. We receive the dictionary of dictionaries with all the data, which indicator we want, the list of countries, and the years. Now we're going to create a matrix. We can use this full method, which creates a matrix with the dimensions that we specify and fills it with some number that we provide. So we're going to create a matrix that has as many rows as the number of years we are asking, and as many columns as the number of countries we are asking for. And we're going to fill it with not a number. So we're going to assume there is no data for any of these values. And now we're going to go through all the different years. We can use the enumerate constructor here that, remember, gives us iterates through all the elements in the array that we provide here, but it also gives us the index. So 0 will be the first year that we have on the list, 1 will be the second, and so forth. This way we know which is the position in the matrix that we want. That is, this index will tell us which row of the matrix we are in, and the year will tell us what year that row corresponds to. And this comes from the list of years we provide here. And now for each country in the list of countries, we also need the position of the country, because this will determine the column in our matrix. And we're going to go through all the countries. And now for each of these pairs, note how these two for loops are nested, which means that for each iteration of this for loop on the outside, we're going to do the whole set of iterations on the inner loop, and then we're going to repeat and repeat and repeat until we go through all the year. So for each year, we're going to go through all the countries, and we check if we have this year in the data for this country. So if this year is present in the dictionary for this indicator in this country, then we're going to place in the matrix at these coordinates, the row corresponding to the year and the column corresponding to the country, we're going to place the data that we have for that indicator, for that country and that year. If the year is not present for that country in that indicator, then this statement will not be executed, and the value that will be left in the matrix is the original one, which is not a number. So this means that whenever some value is missing, we will have not a number in the matrix. And this is an example of a more general idea, which is you have everything structured in memory, in this case those dictionaries, and now we need some part of the data. We create an auxiliary function that gets us the data we want in the convenient format that we like. So this is what we do here. We don't need to change anything else about the program. We just have this additional function. So now we can test this. We load all the files. Note that this will give us a dictionary with all the indicators that we have in this data folder. If you include more Excel files from Gapminder, you will get these additional indicators. Now we create a list of countries, for example, Portugal, Spain, Italy, and Greece. A list of years. We can use this range from Numpy. This will give you an array with the range that you specify here. So this is from 2000 through 2010. Note that the last one, you never reach the last value here. You stop one before this one. So you get from 2000 to 2010. And these are the years. These are the rows in our matrix. And these countries are the columns in our matrix. So the first column is for Portugal, the second for Spain, and so on. The first row is for 2000, the second row for 2001, the third for 2002, and so forth. So this allows us to get just a matrix with just the data that we want. So let's see how we can use this. We're going to create a new module. We're not going to change this original module where we have the functions to process Gapminder, but we're going to save this original module as gapminder.py. So we can create a new module and import the original one, Gapminder as GM. So this is the one that we wrote in these functions here. So loading the data and so forth. And now we can use our module that we created as a toolbox to help us process the Gapminder data. We're also going to load Numpy to be able to use these methods from Numpy. And now we're going to use from our Gapminder module the load all files function that we created. This loads here into this object a dictionary with all the indicators that we have in our data folder. Now we're going to create two lists of countries, northern countries and southern countries in Europe. And we're going to choose these 10 years from 2000 through 2010. And we're going to get the values of GDP and population from for the northern countries. So you see, we use the get indicator values of our data. We want the GDP for these northern countries and just this set of years. This will return a matrix similar to this one with the GDP for the northern countries. And now we get the population for the same countries. So we just use the same function, the same data, the same countries, the same years, but we ask for the indicator population instead of GDP. And now we get another matrix with of the same size, but with the population for each country. And if we want the per capita GDP, we just divide the GDP of each year for each country by the population of each year for each country. And this we can do easily because since these matrices have the same dimensions, Numpy will just create a new array with the same dimensions, but doing the operation element by element. So we get all the ratios between GDP and population for all the countries and all the years. We do the same for the southern countries. And now we can take the average for each year of the southern countries and compare it to the average for each year of the northern countries. So the way we can do this is to use the mean function, but project along the columns. So remember that we have years in different rows and countries in different columns. So if we are projecting in this direction along the columns, we are taking the mean of all the values for the same year over all the countries. And then we're going to do the same for the second year, for the third year, and so forth. So this gives us a vector with all the years by averaging all the countries in the same year for the northern countries. We obtain the same vector for the southern countries, and when we compute the ratio of the two vectors, we get the ratio of the per capita GDP of the northern countries divided by the per capita GDP of the southern countries for each year. So this is an example of what we get here. We get 1.5 in 2000, 1.55, 1.52 in 2001, and so forth. So this seems to be decreasing until we get to about 2007. Then there was that credit crisis, and it increases again. So it seems that before the collapse of that credit bubble, the southern countries were improving with respect to the northern countries. At least the ratio was reducing, but then there was this big crisis, and things went back again to higher ratios. And we can also look at the matrices. For example, this is the per capita GDP of the northern countries for each country on each column, and for each year on each row, the southern ones, and so forth. Okay, so this was an example. I'm going to focus very much these lectures on examples, because the idea is not just to give you the theory, but to actually show you how to work with the data to automate things. So what we saw here was using dictionaries to organize data from the Excel files. In this case, we use dictionaries because we have country names, we have missing values, we have different indicators, and dictionaries are very flexible to organize all of these things. However, if we want to compute statistics, then it's a good idea to have everything into those arrays, because then it's much faster to compute values, to compute statistics, and so on, using the Numpy arrays. So we, after creating this set of functions for reading the Excel files, we created an auxiliary function for extracting the data that we want, and now we put everything in a toolbox, that gapminder module, that we can reuse to work with the data whenever we want. So this is also a general approach that I want you to think about when you are writing your own code, how you can create a useful toolbox that you can then reuse and save you lots of trouble and additional work when you're trying to work with the data. If you want, you can look at this quick start tutorial for Numpy. Gives you several examples of broadcasting, of creating arrays, and so on. But in any case, the most important thing is for you to have an idea of what you can do with the Numpy library. And if you have, if you're trying to do something and you don't remember exactly how to do it, it's easy to go on Google and look for examples and then adapt them. So as long as you have an idea of what you can do and understand enough of Python to be able to read code, you can quickly solve most of the problems just by looking at examples online. So let's take a short break. We continue at 6 o'clock with the second part. Okay, see you soon.